like you got
All right, y'all ready? Get started. So as of right now, we do have an exam that is scheduled for this upcoming Tuesday, a week from today. And it's supposed to cover everything that we've done, 6.2, 6.3, 6.4, which is trig integrals, trig substitution, partial fractions, and then also definite integrals, which we started last class, and then also 6.6, which is called improper integrals, which is what we're going to cover today and on Thursday. So with that said, hope you all are doing well. All right, so we talked about the definite integral last class. Pretty much we established that when we put these numbers here and here, that what that's doing is it's fixing an interval, and we're looking at our function between that interval, and we're able to calculate the actual area underneath that function, right? So there's a big difference when we put numbers here as opposed to when we don't, right? So what are some of the properties of definite integrals? So I've got them listed here. We'll go through them. We'll try and rationalize them, see if they make sense. So the first property says that if you integrate from a to a of any function, doesn't matter what the function is, that your answer is 0. Does that make sense? Because if you go from a to a, that means you're not going to 2 different points, right? So you're basically looking at a single point and you're trying to find the area underneath that single point, and you don't have area then, right? So it makes sense that that would be 0, okay? Now this one's kind of interesting. This one says that if you want to find the definite integral from a to b of some function, that it's equal to the negative of the integral if you go from b to a. It means if you switch your numbers, like let's say this goes from 1 to 4, you get an answer. If you go from 4 to 1, it's that same answer but negative. And that has to do with the fact that when we did these little rectangles, the width of each rectangle we said was b minus a over n. I don't know if you remember that from our formula. But when we go backwards, okay, then these switch places and this becomes a negative number. So instead of getting a bunch of positive little widths, you have negative widths. And so when you get the area, it switches the sign of everything. So that's a property. All right, this one we kind of, well, I don't think we've ever really looked at something like this, but we know what the antiderivative of a constant is, right? So I'm using k here instead of c, because c, we've always done plus c as a constant of integration. I don't want us to confuse it. If we're integrating a constant from a to b, then your answer is just a constant times b minus a. And the way you can see this maybe is look at this example right here. It looks like we're going from -3 to 3. Okay, so here's -3. Here's 3. And this constant function looks like it's the constant 2 function, right? So if we're integrating that, the antiderivative of 2 is what? 2x. And then we put that bar here, and we put -3, and then we put 3, right? Then we plug in 3. We plug in -3, yes? Subtract. Well, this is saying, look, basically you're finding since it's a constant function, you're just finding the area of a rectangle, aren't you? And the height of the rectangle is what? How tall is this? In this case it's 2, but in this case it would be k, wouldn't it? So that's your k, and then how long is your interval? It's b minus a, right? That's how long that is. So if you just multiply the length of the interval times the height of the constant function, you get the same answer. All right, just properties. These are just things that we should note. Property 4. Property 4 we have seen. Property 4 says that if you have a constant in front of a function, that the constant can come out. That we've done, right? So that's not a surprise to see that property. All right, the next one is a little more interesting. It says if your function is greater than or equal to 0. That means when you graph it, the function is above the x-axis, right? Isn't that what it means for a function to be greater than or equal to 0? When I graph it, like this function here is always greater than or equal to 0. It's above the x-axis. If that happens, then this integral should be greater than or equal to 0, which means we should get a positive area. Would you agree with that? Because it's above the x-axis, if we find that area, that's going to be a positive number. Property 6 is the opposite of that. If your function is below the x-axis, so let's say your function's down here like this, and we try and find this area down here, then that area is going to be negative. So the integral will give you a negative result. And we talked about that last time with what? Sine. When we graphed sine, we saw that when we did the second part, it canceled out. So this property is just stating that. Questions? All right, the seventh property. This property comes in, actually turns out to be kind of useful sometimes. It's going to be useful in the next section in 6.6. It says, let's say that you have three numbers, A, C, and B. All right, A is less than C. So I'm going to label these, even though you can see this is 1, 2, and 4 here. This is A. I'm going to say this is C, and this is B. Do you all agree that A is less than C? Yes. And that's less than B, right? So it says if you want to do the area, this is the area under the curve, right, between A and B. So if you want to find this whole area from here to here, you are allowed to split this up into two integrals where you go from A to C first. So we can just find that area and then add to it from C to B, so that would be from here to here. So we are allowed, according to this property, to take an interval and split it up into small intervals if we so desire. All right? All we need is that these numbers right here, A, C, and B, would satisfy that string of inequalities right there. All right, this one is very nice. First thing for this property says if f is an even function. So if f is even. So we have to talk about that. Make sure you remember what it means for a function to be even. Does anyone remember what it means for a function to be even? Yeah, it's something about reflections. Okay, so even functions, just to remind you, an even function is a function where f of x equals f of negative x. Any function that satisfies that is an even function. So if we look at this, what this is saying is that when you plug x into this function, like for example, this looks like this is 1, right? You see that's the number 1? If I plug 1 into this function, I get the same thing as if I plugged in negative 1. So where's negative 1? Right here. So do you agree that this y coordinate, the function's value at 1, is equal to the function's value at negative 1? And if that holds for all values, then it's called an even function. So if I go to 2, here's 2, plug in the value, I get this. But if I plug in negative 2, I get this, and I get the same y coordinates there. So even functions have to satisfy that equation. But visually, what are they? Yeah, all even functions are reflections of themselves over the y-axis. So if I take this function, I mirror it over here, it's going to land right on top of itself, right? Agreed? Okay, so if f is an even function, okay, we're assuming that f is even. So if f is even, then the integral from negative a to a, so if you go from any point, negative a to positive a, then the answer is twice the integral from 0 to a. Does that make sense that would be true? Yeah? So it's like, look, if that's a mirror image, then all I have to do is go from 0 to a, figure out what that area is, and double it, because it's the same thing over there. That kind of make sense? Okay. So that's a pretty convenient little thing. The next property has to do with if a function is odd. So let me talk about odd first. For odd, what we need is this. So this is what it meant to be even, right? That was even, right? The only difference between even and odd is that this is negative here. So what does that mean visually? Let's take a look. So take a look at this one right here. Let's say I plug in x is 2 here, right? Plug in 2 here. Is that equal to f of negative 2? Now I didn't put the negative here. This would be even, right? Is this the case? So I plug in 2, I get an answer, right? When I plug in negative 2, I get a different answer. This one down here, right? These are not the same. However, they are related somehow. This one looks like the same distance, just negative, right? So if you add a negative out here, then this is true, right? So the function's value at 2, as long as you change the sign, would be equal to the function's value at negative 2. Yes? Sure? Okay. So what do they look like visually? They're not reflections over the y-axis, right? Odd functions do not reflect over the y. What are they then? Reflection over the x-axis would be here. Over the origin. So what does that mean, to reflect over the origin? Yeah, it's basically a double reflection. It's over y, then x. Or you can go over x, then y. So if I reflect this piece over the y-axis, it's here, right? And then when I reflect that over the x-axis, it lands here. So odd functions are like double reflections, over y, then x. All right? Now, look at the property. If f is odd, and you want to integrate, find the area from negative a to positive a. So that means if I went from here, if I took this area and this area and add them up, what should I get? 0, right? That should always happen. So there is a problem in the homework that's somewhat difficult. I think I told you not to do it. But it was an integral, and I don't remember what it was from, but I'm just going to make it up. It went maybe from like negative 3 to 3. And then the thing here, this function in here, was very complicated. Actually, you can't integrate it, all right? Like if you tried, all your techniques would fail. And so what you have to actually do for this problem is realize you're going from negative a to a, and you actually have to show that that's an odd function. You have to show it. So once you show that this is an odd function, then you can say that the answer is what? 0. All right? So let me show you how you show something is even or odd. Can I do that? All right. Because I think that will come up at some point. So I'm going to give you a specific example. All right. Example, I'm going to give you a function f of x equals x to the 4th minus 3x squared over x. Let's do that. Is f even, odd, or neither? Because it is possible, when someone gives you a function, it does not have to be even or odd. It's not like there's one or the other. It can also not be either one. So is this function even or odd or neither? So how do we do it? How do we actually do this? To show that it's one or the other or neither, what we do is this. First we check, is it even? Right? Is it even? So does f of x equal f of negative x? Right? That's the question we're asking. All right? So let's see if that's true or not. First of all, what is f of x? Well, we know that, right? F of x is given to us. Okay, that's f of x. Now, what is f of negative x? So you replace all your x's with negatives, don't you? Negative x's? So that means I would go negative x to the 4th minus 3 times negative x squared all over negative x on the bottom, right? Now what happens if I take a negative number and raise it to the 4th power? It's still positive, right? So that that piece right here is still just like x to the fourth because the negative doesn't matter. Then I have minus 3. Then what happens if I square a negative? It's going to be positive, so that's x squared. And then over, what, negative x? See, I'm not squaring that, so it's just going to stay negative x. Are these the same? Well, the numerators are identical, aren't they? The numerators are, but the denominators are off by a sign. And so these are not the same, are they? So this is not even, right? Not even. Now, is it odd? Is it odd? So we need to check, is negative f of x equal to f of negative x? So that's what you have to check anytime you want to see if something's odd. So let's start out with the first statement, this first one right here. What is negative f of x? Well, that's this negative, right? Yes? Which means I need to put a negative in front of this. So why don't I distribute the negative through the top? Put negative here, and that would change that to a positive, wouldn't it? Y'all see what I'm doing? Yeah. Okay. And now we need to compare this to what? F of negative x, right? Which is this one. Are these the same? Are they? So I'm hearing yeses and nos.
Yes.
Yes? Okay, so when you have a negative on this x here, think of it like this fraction. If I write the fraction 1 over negative 4, that's the same as negative 1 over 4, isn't it? And that's the same as negative 1 over 4. All those are the same, aren't they? Like the negative sign here can kind of float. It can go out front or up on top, right? So if I take this negative sign right here, obviously this is positive and this is negative, right? So if I take that negative sign up here and then push it through the numerator, what do I get? Negative x to the fourth, right? Plus 3x squared all over x. And look, this is odd, right? These are the same, right? So this is an odd function. So to show something is even or odd means you have to check whether or not, those equations are true. That make sense? Okay. So if you were asked to integrate this from negative 10 to 10 of x to the fourth minus 3x squared over x dx, yes, we could do this. We could actually, this one we could split into two different integrals, right? Because it's like this over this, and we could just use power rule. But there's really no work that needs to be done. If we know that this is an odd function, which we would have to verify, then we know the answer to this is 0. All right, so there's a problem like that in one of the homework sets that you'll run across. And so the way you'll know to kind of be looking for it is these will be the same numbers, just negative and then positive. Now, what if I change this to 5? You can't do it, right? The property only works when you go from negative a to a. So you'd actually have to integrate this one. You'd have to do it by hand. Okay? Questions on that? All right, so that is the official, I guess, suggested homework that you should do that would get you kind of up to speed on this definite integral. So what I've done is I've gone back. Some of these assignments you've already done. All right, so let me double check that. Let me see. 280. I don't think I have the most recent one. Who has the printed out list of homework problems? Anyone have that? You have it? Let's see. See if any of this is stuff we've done. .307, what? Yeah, so I think like, what? 326. Yeah, so some of these, like this and this, we've already done these problems, but these are the ones that had the numbers, and you should just go back and revisit those. So, I mean, don't like kill yourself over this thing. It's all I want you to do is be able to go back, look at some of the problems you've already done, plug the numbers in, just practice doing the calculation of capital F of B minus capital F of A, the stuff you have to do for a definite integral. All right, and with that, I think we're going to move on. Those are the properties. And now we're going to use them, but we're going to really kind of take a big leap here into 6.6. All right, so we are going to talk about improper integrals. Now, improper integrals fall into two categories. We have type 1 and type 2. The first type are what we call infinite intervals. So, I mean, what we can, I guess, say we've established is what I put up here earlier. When we do this, this means the area underneath this function, or between that function and the x-axis, on the interval AB, right? That we've done. But now we're going to go and we're going to start having infinite intervals instead of, like this is just a closed interval from A to B. Now our intervals are going to be infinite. So that means they're going to be infinitely long. So all of our integrals are going to look like one of these three then. We're either going to be integrating from a number to infinity, which means A to infinity, or we're going to be going from negative infinity to some number B, or if we want to just blow the doors completely off, we'll just go from negative infinity all the way to infinity. So that means this is saying, hey, look, here's a function, right? Find the area between that function and the x-axis, between A and infinity. So that means you never stop, like you just keep going forever. And this should be somewhat problematic. Like you should have some problems with this idea. Because if it keeps going forever, it would seem like the area would be infinite, perhaps. All right, so how are we going to do these? So I have some visual aids here to help us understand what's going on. So here's an example of a function in blue. Now notice that this function is asymptotic, right? It's approaching 0, isn't it? That function is approaching 0 as you move to the right. So if we want to try and find the area from A, right? So this A is 1 here, but we'll say from A, and you want to go forever. Now, of course, I have to like zoom in to see it, but you get the idea that this just keeps going forever? Okay, so if I want to know the area underneath that curve forever, then this is what the integral is going to look like, A to infinity, but this is what we actually do. This is the actual mechanical computation. What we do is we go from A to T, not A to B, right? We go A to T. We figure out what all this is, okay? So that's a definite integral. Like A to B was definite. So we're going to do that, and then once we're done, we get an answer. It won't be a number anymore. The reason it won't be a number is because this is going to be a variable. This one will be a number, okay? This might be like 1 or something. But that will stay T. We'll get an answer, and then once we look at that answer, we're going to take the limit and let T go to infinity. And that will represent the area. That sound fair? Now, if we want to go and do this type that goes from negative infinity to B, that means that our picture looks like this. Here's B. Negative infinity is that way. Again, we have a function that's asymptotic. We're trying to find the area underneath it. To do this, we're going to replace the infinity symbol with T. We're going to leave B as B. We're going to figure out what this is, but at the end, we will let T go to negative infinity. So it's kind of like what we're doing is we're finding a definite integral, we're stopping it, and we're looking at just the area from T to B, but then we're going to let T go to negative infinity. That's what we're doing. And then this one, oh, well, I should say, let me see, did I say that earlier? I didn't. Okay. So do you see that to do these improper integrals, we have to take limits? And do you remember that in Calculus 1, when you were doing limits, it was possible to get an answer that the limit does not exist? Okay. So this next part of the note says, if these limits exist, okay? So if we take a limit and we get an answer, then we will say that the integral is convergent. If these limits don't exist, we will say that the integral is divergent. So these are new words for us. We're going to start using these, and we'll use them again in Chapter 8. This idea of convergence and divergence. So convergent, I think, for us should mean that that area underneath is going to a number. All right? It's going to something. Divergent means that that area is not going to something. I'm not saying that it has to be infinite. I'm just saying it's not going to something. Let me see if I can help you with this idea. Let's take a look at the sine function. All right? Now, what do you think the integral would be from 0 to infinity of the sine function? Think about this just purely from a geometric standpoint. That's the area underneath this curve, right? From 0 to forever. So I want this area, 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 right? Forever? Do you think that this integral is going to be convergent or divergent? Why divergent? They will cancel each other. If they cancel each other, wouldn't you just get 0 though? And that would be convergence. If it actually went to 0, then that would be convergence because it's converging to a number. It's going to something, right? 0 is a number. Okay? But that's not what happens. Yeah, see, when you go to infinity, you're never stopping, are you? Right? So imagine if I keep going, I keep going, I keep going. If I stop somewhere, right? I might have, if I stop, let's just say, like, tell me when to stop. Okay, right there. Okay, so right there, you told me to stop right here. If I stop right here, okay, then I'm actually going to have, it looks like these will cancel, right? These will cancel, and then here I'd have a little bit of positive. So I would have got a positive answer, wouldn't I? So now I keep going, and then someone tells me to stop, and I stop, and now I would get, I don't know, maybe a positive answer, maybe a negative, right? Depends on where I stop. The idea is that as I keep moving out, right, as I keep moving out, this area keeps fluctuating, right? It is 0 sometimes, but then sometimes it's positive, sometimes it's negative. So this fluctuation means that the total area out this side is divergent. I don't know if that makes sense or not. We'll investigate it some more, but I just want you to understand that convergence means that it's going to a number. That means the area is actually approaching something, and divergence means not convergence. Sometimes divergence means infinite area. Sometimes it means something like this, where it's just kind of fluctuating. We'll get to practice more. All right? All right, finally, if we want to go from negative infinity to infinity, right? If we want to look at the area underneath the graph, going out both directions forever. Okay, so this total area, this way and this way forever. Then what we're going to do is we're going to use one of those properties of integrals that allows us to split it up into two. So what we'll do is we'll first go from negative infinity to a. So that means we'll go from negative infinity is like way out there, right? And we come here and we just pick some point A. It can be anywhere, all right? Like here's A, right? And what we'll do is we'll find the area of that, which is this integral, and then we'll add to that from A to infinity, which would be on this side. So we split it into two. And these two integrals will each have to be done with a limit. So this looks like the one from before, and this one looks like the one before that one. So each of those will have to do a limit on those. All right, let's do an example. I mean, the only way to understand this is get your hands dirty, right? So we're going to take a look at this function, 1 over x squared. Do I have a graph of this? I don't. Okay. 1 over x squared is, what? Yay, where did you hear that? All right, good. Yeah, it's called the Volcano Function. I don't know if it really is, but I remember it being called the volcano function by someone. Okay, it looks like this. And the function is asymptotic. Now, what that means is if you let x go to infinity, okay, right now, if I start moving out this way, what is the function doing? It's getting closer to 0. And you can tell because look at the function, 1 over x squared, right? If I look at 1 over x squared and I let x get huge, right? Then this ratio, 1 over a huge number, is going to get very small. So that happens whether or not I go out this way or this way. But we're only interested in the area from 1, right? So like right here, out this way. But forever, right? Forever out that way. Well, according to the notes, here's what we need to do. This will be equal to a limit. And what we're going to do is we're going to let t go to infinity. And we're going to rewrite the integral. And what are we replacing with t? That infinity, right? Pardon?
Because you said, what are we replacing? Yeah, you mean, what are we replacing?
What are we, yeah, I don't know. What did I say? Did I say what are we replacing t with?
Yeah.
Yeah, that's not what I meant. What I meant is, what are we going to replace with t? We're going to replace the infinity with t. So the upper limit of integration, right? This limit of integration that was infinity is now going to be the t, and then the bottom one is still 1, right? And then we have the actual function here, which I'll rewrite that as x to the negative 2, right? So let's work this out. Next line, I write the limit again. Because I have not taken the limit, since I have not taken the limit is going to follow me through my work the whole way through, okay? Now, let's do the antiderivative of this. The antiderivative of that is what? Should be negative 1 over x. Negative 1 over x. So this is going to be negative 1 over x, right? That's the antiderivative. And then from last class, because it's a definite integral, we put the bar here. Sometimes we call that the evaluation bar. And then what do I put on the bottom? 1, and on top, t. Okay? Now, the next step, we rewrite the limit again. T goes to infinity. And now we do our plugging in game. So I'm using the fundamental theorem of calculus from last time, the evaluation theorem. And I have 2 sets of parentheses, and I'm plugging something in here. So first I plug t in, right? So I rewrote the limit. I'm going to plug t into this for x. So I get what? Negative 1 over t, right? And then over here, I plug in, I replace the x with 1, right? You get that. So you get negative 1 there. So now this is really just, I'm going to rewrite it one more time. Limit t goes to infinity of, this is negative 1 over t, and then minus minus is plus, so you get plus 1, like that. Now we let t go to infinity, right? So what happens if t goes to infinity? So we're going back to Cal 1 now. We have a number that's fixed, right? This is a constant over a number that's going to get huge. This ratio should vanish to 0, right, in the limit? So this expression goes to 0. This expression doesn't have a t in it. So it's just going to stay what it is. So the answer is what? 1. This integral converges. It converges to 1. That means if you were able to calculate the area under this forever, it would be 1. That's what it would be. Now, you can't ever do that, right? I mean, like, you would have to stop somewhere. Maybe you stop at 1,000,000. Okay? That's not 1,000,000. Maybe you stop at 1,000,000, all right? If you go from 1 to 1,000,000 right now, here's what I can guarantee you. That number's going to be really close to 1. All right? It's not going to quite be 1, though. It's going to be a little smaller than 1. Because you have to go forever to get 1. Yes?
So instead of writing equals, why don't we write the little like squiggly lines?
Great question. Great question. The question is, why don't we write squiggly equals? And the reason is because, do you remember in Cal 1 when we took limits and we said that the function was approaching something? Right? We never, when we did a limit in Cal 1, we never put squiggly equals, like the limit was something squiggly equals. We would say the limit equals 4. And what that meant was that the function was approaching it, right? We were never saying that it ever got to it. And that's what we're saying here. This integral right here converges to 1. It's going to 1, right? The further you go out. The problem is you can't go to infinity, right? It's impossible to go to infinity. Infinity is an idea. It's a concept, right? It's an idea. It's not a number. You can't never go to it. I've always thought this is somewhat mind-boggling because, you know, you have area out here, right? No matter how far you go, you've got a little bit of area, don't you? So if you go a little bit further, you're going to have a little bit more area. A little bit further, a little more, and you can get to go forever. So how is it that this doesn't, you know, why doesn't the cuppeth filleth overeth? You know what I'm saying? It doesn't happen here. It can't overfill 1. That area added up together forever cannot overfill 1. It's kind of, does that not bother you? It's counterintuitive, okay? I think for most people it's counterintuitive. And as we're going to see, it all depends on how fast that function is approaching 0. Like that function dives down to 0 very quickly here. And it's the rate at which it actually comes down that determines whether or not we are going to have convergence or divergence, as demonstrated in the next example. So if we look at the function 1 over x instead of 1 over x squared, that still kind of looks like this. It's not exactly the same though. It looks like, this side still looks like this, but the other side is negative, so it looks like that. But that's not really relevant to us here, because we're only looking from 1 to infinity again, right? So we're looking for this area in here. Now that function does go to 0, right? Listen to what I'm saying. The function goes to 0 as I go out to infinity, right? The function does? Yeah. What does the area under the function go to? That's what we're about to find out. So even though the function goes to 0, that doesn't mean the area, that doesn't tell us anything about the area. So let's do this. Set it up, beginning. Limit, right? Limit t goes to infinity. Integral 1 to t of 1 over x dx. Equals limit again. T goes to infinity. And I think at this point we can actually do the antiderivative. Antiderivative of 1 over x is what? Natural log of the absolute value of x. And we're going to use our evaluation bar. We're going to put 1 down here and t up here. And then I write the limit again. Limit t goes to infinity. And now I'm going to have 2 things that I have to plug in. And I'm going to subtract them. So what happens when you plug t in for x? You just get natural log of t, right? Absolute value of t if you want. What happens when you plug in 1? You get 0. Why do you get 0? Because the natural log of 1 is 0, right? That's one of those things from somewhere in the past you should just know, right? All right.
Natural log of any constant.
No, natural log of 1. Yep. But any log of 1 is 0. So, natural log of 1 is 0. Log base 4 of 1 is 0. Any log with 1 plugged in spits out 0. And it goes back to the idea of what does it mean? Okay, so what this means, like log base 4 of 1 means what power do I raise 4 to in order to get 1? Well, you have to raise it to the 0. This natural log is really log base e. So what do I raise e to in order to get 1? Well, e to the 0. So 1 plugged into any log gives you 0. All right, but we're not done. We now have to do this. The limit as t goes to infinity of the natural log of t. What does that mean? I'll tell you what it means. It means you need to know what the natural log function looks like. Okay, so I'm going to go back to college algebra here, and I'm going to graph the natural log function. The natural log function looks like this. Of course, this is 1. That's where x-intercept is, because when you plug in 1, you get 0. And then it kind of goes to the right like this. Does that look familiar? That's your natural log function. Some important things about the natural log function. It's not defined to the left of 0, right? Like the natural log, you can't plug negatives into logs. So there's no graph over here. What about at 0? It's undefined. Natural log of 0 is undefined. But if I were to ask you, what does the natural log function do as you approach 0, you would tell me that it goes where? To negative infinity, right? So if this argument in here, t, if t was approaching 0 from the right-hand side, the function would dive down to negative infinity, right? But what is our argument approaching? Infinity. So that means we're going this way, right? So what is my function doing as I go to infinity? It's increasing. Now it's getting bigger and bigger, right? So well, let me go back here. So if it's here, it doesn't grow real fast, but it does grow, and it just keeps growing forever. So as you go to infinity, the natural log function also goes to infinity. So that means this is going to go to infinity minus 0, which is infinite, right? What does that mean? It's divergent. This is a divergent integral. So for this one, as we start to add up the area, we keep on going forever and ever, we actually overfilleth the cuppeth, all right? It actually overfills this one. And it's just, again, because this is just not, it's just not shrinking fast enough, where 1 over x squared did shrink fast enough. Any questions on that? Yes?
Did you say overfill the cuppeth?
I said overfilleth the cuppeth. Yeah, we've been getting pretty advanced in here. You came in a little late, and so we are doing some experiments with English in here. Yes.
Do you say the area is infinite, or you say...
Okay, great question. In this particular problem, it appears that the area is becoming infinite, right? Because our answer is infinity. But you would just respond by saying interval is divergent. Because divergent can mean for us 2 different things with this. It can mean it's becoming infinite, or it can mean it's like oscillating, but it's not headed to a number. So to make things easy, if you get an answer of infinity, just put divergent. No, you don't look happy with that. It's weird. Okay, does convergence...
The area is infinite, but integral is divergent?
That's right. An infinite area means divergence. Okay? Convergence means the area is finite. Convergence means the area is finite. So in the previous answer, we got what? 1? The area is 1. That's convergent. It's going to a fixed finite number, 1. In this problem, we got an answer, right, of infinity, but infinity is not a finite number. So what happens when your answer is not finite? It's divergent. So I want you to look at divergence this way. Convergence means it goes to a finite number. Otherwise, any other scenario, divergent. Okay? And infinity is not a number. It's not a finite number. All right, look at this one.
So, sir, even if it does not exist, that will be divergent.
That's right. If we take a limit and that limit does not exist, we will say divergent. All right, what about this one? Look at our limits of integration. We're integrating over the entire number line. Everywhere, right? All the way forever that way, all the way forever this way. We're trying to find the area under that curve. Now 1 over 1 plus x squared, I'm not quite sure if you've ever seen that graph. I'll graph it for you real quick. Maybe you can help me. What happens if we plug 0 into that graph? What do we get? We get 1. So it's 0, we're at 1. And then what happens if we plug in 1? We get 1/2, right? So if I plug in 1, I get 1/2. What happens if I plug in -1? I get -1/2. I mean, not -1/2. Sorry, I listened to you, but I wasn't thinking. Positive 1/2, right? -1 here, you square it, you still get 1.
Yeah.
So 1/2. So this is actually an even function. The same thing's happening both directions, right? Okay. And if we plugged in, let's say 2, what would happen? 2 here, 4, we get 1/5. We plug in 3, we're going to get like 1/10. So what's happening is as we go out this way, it's getting smaller, right? And the same thing's happening that way. So it actually looks something like this. Kind of like a bell. It's kind of like a bell curve. So we would like to know the area underneath the entire thing. So the way we do this, because we're going from -infinity to infinity, we have to first rewrite it from -infinity to any number that we want. And then from that number on forever. So a nice number between -infinity and infinity is 0. You can use 1, you could use 2, you could use any number, but 0 is a nice number. Would you agree? So we're going to do that. We're going to first go from there, -infinity to there, and then plus, right, the integral from where to where? 0 to infinity of the same integrand, the same function. And then each of those we have to do with their own limit. So on this first one, I'm going to say limit as t goes where? -infinity. And then my integral is going to go from where to where? T to 0. And I'm integrating 1/1 plus x squared dx. And then plus, now another limit, right? Different limit. Limit. Now I could use t again, as long as I remind myself that this limit is completely separated from that limit. Like they're two different limits that I'm doing here. But so I don't confuse myself, I'm just going to use, how about s? S goes to what? Infinity this time, right? And then integral where to where? 0 to s. Do y'all see I'm using s instead of t just because I don't want to mix up my t's and be thinking two different things? Okay. And then 1/1 plus x squared dx. All right, next step. I have to write limit again. Limit t goes to -infinity. And now I think I can try and take the antiderivative of this. You can, right? What's the antiderivative of 1/1 plus x squared? Arctan of x. That should be one of those ones you remember, right? Arctan x. So this is arctangent of x. Now my evaluation bar, what goes there? 0 on top, t on the bottom, right? Then I have plus another limit. This time s goes to positive infinity. Is it the same antiderivative? It is. Arctangent of x in my evaluation bar this time goes where? What do I have here? 0 on the bottom, s on the top, right? Do y'all see how this is all getting set up? Any questions on this? Okay, I need another line here. I'm running out of space. So this is going to become equal to, all right, got to write the limit again. You know, just the way it goes. All right, now I'm going to do this first evaluation right here. So I'm going to need a set of brackets, maybe 2 sets of parentheses here like that. Are you kind of understanding why I'm what I'm doing? I'm doing this every time. I'm doing like a bracket, 2 sets of parentheses, and then I'm going to plug in what 0 goes in first, right? And then t goes in. So I'm going to have arctangent of 0, and then arctangent of t. What do I write next? Plus another limit, right? S goes to infinity this time. Bracket, parenthesis, minus parenthesis, bracket. Arctangent again, I go S and then I go 0. So arctangent of S, arctangent of 0. Now some of these we can handle right now without taking any limits. What is arctangent of 0? What is arctangent of 0 really saying? Isn't that saying tangent of some angle is 0, right? No? Arctangent of 0 means we're trying to figure out what angle you take tangent of to get 0. So this is really saying tangent of some angle, I'll call it theta, equals 0. You know, what's that angle? That's a question mark. 0. It's 0. All right? It might help you if you actually know what the tangent function looks like. So I'm going to graph the tangent function for you real quick. You took pre-cal, right? So you remember this? This is tangent. This is your tangent function. That's tangent. That's not arctangent. That's tangent of x, right? So when we say arctangent of 0, what we're saying is what x value do I plug in to get 0 to come out of this? And that's the origin. That's 0. So this is 0, isn't it? And then so is this one. Just for kicks, what's arctangent of 1? Pi over 4. Pi over 4. Okay. You have to use the unit circle if you want to get it that way. You're looking for where your ratio is 1, so that happens at 45 degrees, and that's where your sine and cosine are the same. And okay. Arctangent of negative 1? Negative pi over 4? Okay. Now, let's take a limit. Are you ready for these limits? This is going to be kind of weird. Okay, I'm going to let t go to negative infinity, right? So I'm going to be letting that go to negative infinity. What? Arctangent of negative infinity? So that means you come back here, and you know how arctangent of 0 said, hey, where on the x-axis is our y-coordinate 0? This is saying, where on our x-axis is our y-coordinate approaching negative infinity, right? Negative infinity. So where on our x-axis is our y-coordinate approaching negative infinity? Right here, right? At this asymptote. What's that? That's pi over what? Negative pi over 2. And this one is pi over 2, right? So this right here, I'm taking the limit. This is 0 minus, and then this right here with that negative infinity plugged in or evaluated, you get negative pi over 2. And then plus, now we already know that's 0. This is saying, all right, we're going to replace s with infinity. So this is saying where on our graph is our y-coordinate becoming positive infinity. And that would be over here, and that would correspond to pi over 2. So this would be pi over 2, and then minus 0. So what do you get end of day here? Pi. Pi. Pi over 2 plus pi over 2. The area underneath this curve in both directions forever converges to pi. Strange, right? but that's the way it is. Do y'all see how this inverse thing worked? This is kind of strange. We're taking the limit of an inverse trig function. And even though pi over 2 cannot be plugged into the tangent function, this is a limit. So we're saying, where is the function approaching? The function has to approach negative pi over 2 in order for its value to approach negative infinity. So the closer this t gets to negative infinity, the closer this value gets to negative pi over 2. So as we go out t that way and t that way, these two numbers get closer and closer to pi over 2, and that means when you add them, it gets closer and closer to pi. All right. Now, you might think that these functions are ridiculous, like why would you ever need this, right? I think it might be time for us to talk about why you would ever want this. Convergent, yes. Was the answer a finite number?
Yes.
Convergence.
So if the answer was E, that would be a convergence.
That's right, because E is a finite number. Doesn't matter that it's an irrational number. Just as long as it's not infinity, negative infinity, or does not exist, we're pretty much convergent. Okay, so let me explain something here. See how I can do this. All right. This is a very, very quick thing, hopefully. You're not going to be tested on this. That doesn't mean I don't want you to pay attention, but probability density functions. Sounds bad, but it's not that bad. Probability density functions. Okay, so I'm going to take a very simple example. Everybody has seen a six-sided die, right? All right, so the probability density function for a six-sided die goes like this. On the x-axis, I'm going to list the outcomes. Okay, so we could have an outcome. If I roll a six-sided die, I could get a 1, a 2, a 3, a 4, a 5, and a 6. Right? Those are the 6 possible outcomes. Now, on the y-axis, I'm going to plot the probability of getting each of those. So if you roll a fair die, what's the probability that you would get a 1? 1 out of 6, right? So if this is 1 up here, 1/6 would be maybe right here, let's just say. So that would be the probability of getting a 1, yes? Probability of getting a 2, 3, they're all the same, aren't they? Okay. Now, if I drew a rectangle here, oh, that's supposed to go halfway. Rectangle here, rectangle here, rectangle here, rectangle here, and a rectangle here. Okay? Like that? Each of those rectangles is how wide? I tried to draw them correctly here, but what would you say? Each one is what? About half each way, right? So each of these rectangles, I've drawn them so that they're 1 unit wide. Agreed? How tall are each rectangle? 1/6. What's the area of each rectangle? 1 times 1/6, right? So it's 1/6. That's the area of that rectangle. What's the area of all of them together? 1/6 plus 1/6, 6 of them, right? So the total area of the whole thing is 1, right? Now, here's the way this works. In the real world, okay, if you have something going on, like rolling a die or some sort of, we can talk about other things, but in this scenario, we have 6 possible outcomes, right? That each have a probability for their outcome. The sum of all probabilities must be 1. Do you agree with that? Because this 1 really means 100%, okay? So it's really saying like, look, what's the probability that one of these is going to happen? Well, the total probability has to be 1, total, of all of them together, right? So the area of these actually correspond to 1, yes? Kind of makes sense? Now, let's take something else, like, let's take the average, let's just say we're doing the same thing, but we're talking about people's heights, okay? How tall somebody is.